talk is an almost universal algorithm for global minimum cut. So the plan of the talk is to spend a little bit of time in the beginning to talk about what is global minimum cut and what do I mean by an universal algorithm for it. So let's start with the basics. So the global minimum cut problem is defined on a graph, and the graph can be viewed as any kind of network that you have in your mind. So given a graph or any network, the question is like how many edges that you have to remove to disconnect the network. So more formally, the problem would be, here is a graph, and it has got n many nodes and m many edges, and each edge, let's say, have certain weights. So, and on this graph, a cut is defined to be a set of edges. When you remove them, the graph becomes disconnected. And the min cut question asks is to find the cut where the total amount of edges, not the amount, but the weight of the edges that is crossing the cut is minimum. I should point out that may not be a unique minimum. I mean, if there are more than one minimum cuts, you just have to output one of them. All right, and in this talk, we are mainly interested in weighted graphs. So it means that the edges can have weights on them, and you have to minimize the total weight, as opposed to in the unweighted case when you have to minimize the total number of edges. Okay, and I should point out that some variants of the problems is taught usually in the undergraduate course, where it is usually the ST minimum cut. So in that problem, you have two spatial vertices. Let's call this vertex S, and let's call this vertex T. And the goal is to come up with a cut, or come up with a minimum cut, which separates these vertices into two different parts of the graph. So this is called ST min cut, which is sort of equivalent, not sort of, like exactly equivalent to ST max flow problem by strong duality theorem. And there are a number of algorithms known for the max flow problem, starting with the dynamics programming approach by the Fulkerson, and then more fancier algorithms like Dinix algorithms and preflow push algorithm. Just want to mention this because I want to differentiate the topic of today is that we are not looking at ST min cut, we are looking at global min cut. That means that there is no spatial vertices S and T, you just have to give me a global min cut which has the minimum weight crossing across. All right, so now the problem is set up. Let's look at what is known about this problem. So if you pick up the
Sagnik, I have a question. Yeah, the min cut should. So what is a global min cut? It's like it should dissociate the graph in multiple pieces. Is it? That is what we'll call them. So the number of connected components should be more than one.
Yes, that's all.
Okay.
So that will be a cut.
Yeah,
and you have to find a minimum.
Yeah.
So if you look at the book that is usually taught when a randomized algorithm is taught in the courses, usually, the first chapter has a min cut algorithm on it. So this is by David Karger, and like later on improved by Clifford Stein and David Karger, and which the complexity is n square log square n. So we are always, the convention over here is that n always represents the number of vertices and m will represent the number of edges. I want to mention this algorithm a little bit because it's a very simple algorithm and the analysis is extremely elegant. So the way it works is, so you have this graph, and let's, this is just the way the algorithm works when the time goes from 0 to whatever, bigger time. So this is the graph you started off with. And the algorithm is as simple as the following. Pick any edge uniformly at random. Let's say you pick this edge and you contract that edge. And so you get this graph. And then in this graph, you pick another edge uniformly at random and you contract it. And you keep on doing it until you are left with a graph, a contracted graph here, which has got only 2 vertices left. And you output the number of edges between these 2 vertices, and that is the algorithm. The analysis, however, is interesting, which sort of tries to tell you that by doing so, you will never contract an edge, which is a part of a min cut. And why this is true? Let's just do the analysis very quickly. I mean, this is just to set up this stage. We do not need this analysis for the level, the rest of the talk, but let's just do it anyway. So,
here you are talking about a near linear time algorithm, which is randomized.
Which is randomized, yes. So we are talking about, I mean, this and a few more.
So you have some guarantees saying that. So now, like essentially, this algorithm is there is a guarantee that with a high probability, you will end up, and under this process, you'll end up with a min cut.
Correct. Yes. And I mean, let me just give you a 2-line proof of this. Why this works. So the probability that you are gonna actually contract an edge of the min cut is going to be the size of the min cut. Let's call that lambda by the number of edges of the graph. Right, and let's, for the time being, let's just assume that the graph is a simple unweighted graph, so there are no weights on the edges, and the same kind of analysis also works for weighted graphs as well. So now, let's look at what is E. Right, so E is going to be the summation over the degree of every vertex divided by ½ right? This is because you're counting every edge twice. So this is going to be at least half times n times the mean degree, right? And the mean degree is at least lambda, right? Because I mean, if mean degree can be lambda, in that case, the min cut is just going to be a one singleton vertex on one side and everybody else on the other side, but it cannot be smaller than lambda, right? So essentially what you have over here, this is going to be n lambda over 2. So the probability that we have written down, this is that you actually contract is going to be 2 over n. So this is the probability of the bad event. So the probability in this step, you actually the min cut survives is going to be 1 times 2 over n. And here it's going to be 1 times 2 over n minus 1, and so on and so forth. So this is when you multiply them, they sort of telescope and cancel out each other. So at the end, you're left with something like 1 over n squared. So this is the probability that if you run this process once, the min cut will survive. So you run it n squared log squared n many times, or n squared polylog n many times, so that you get high probability event. So that is the algorithm. So just wanted to point this algorithm out because this is very elegant, but unfortunately, we are not going to talk about this algorithm today. We're going to talk about another algorithm by Karger, which is actually close to being near linear. So, and what do I mean by near linear? It means that a linear time algorithm in this scenario is going to be an order m algorithm, which is like order the number of edges. So this is m with a polylog factor in n. So this is very close to linear. And we do not expect that you can get an algorithm which is actually a little of m, because I mean, there is no like a formal reason for it, but the intuition is that if you do not see all the edges, if you do not have time to process all the edges, then you will never be able to find the min cut, because there should be an adversary argument. This kind of intuition is formalized in other models of computations like communication and stuff like that. But for Turing machine model, this is a little bit hard to formalize. But this is what we are looking for. This is the goal. Okay, so, but there is a problem with the Karger's algorithm, not necessarily a problem, but it is, if you look at the paper and if you look at the algorithm, this is actually a very complicated dynamic programming paradigm. And the data structure that they use are very tuned to the kind of dynamic programming that they're doing. So it is very hard to adapt to new computation models, like let's say streaming complexity, streaming algorithms or query algorithms or distributed algorithms and so forth. So this is the state of the art in the sequential model. Means that it's a unit RAM model. So Karger gave an algorithm in 96, which is like a near linear M log cube n. And then there are multiple improvement by Hensinger, Rao, and Wang, and Ghaffari and company, which sort of improves this log factor. But crucially, I want to mention over here is that all of these things are only when the graph is simple. And what do I mean by simple graph? It means that there are no multi-edges, there are no self-loops, and there is no weight on the edge. So it's as simple a graph model as you can think of. This is definitely not for weighted graphs. Okay, so, but in this talk, we would be interested in other models of computation as well. And to be very honest, the whole talk is going to be on some other models of computation. We are interested in like the 4 to 5 models of computation. And I'm going to talk mainly on the first model that is written over here, which is the cut query model. And I will explain what is the cut query model. But we are also interested in semi-streaming models and communication models and distributed models, and as well as parallel models like PRAM models. Okay, so let me just give you a landscape of what was known before. So we are looking at weighted mean cut. That means that the underlying graph is not simple, it's weighted graph. And in this sequential model, we have already seen that these results are known, sort of. In the cut query model, which we will define very quickly, there is an order n algorithm known. In the semi-streaming model, where it's a streaming model, but the working memory is n polylog n. In that model, there are algorithms known which can find the min cut in 2 passes. And in the distributed congest, which I will not define actually, there are like almost as efficient as possible algorithm known. Now, what we do, I should mention that all the things that I've written over here, except for Karger, everything is assuming the graph is simple. Now, you might ask, it's like, yes.
Somehow in this case, you're actually running time in the fourth model is less than n.
Yeah, so, but it's a distributed model, right? So the expected, the goal would be square root n. So the lower bound, we have a lower bound for it, and that will give you an omega square root n. Like, forget about the d part, that's a diameter constraint, that's always crops up, but the end part should be square root n. So that's the goal. Okay, so these are all for simple graphs, but our goal is sort of like to design an algorithm for weighted graphs, because that sort of captures the real, like real life networks and all this thing. Then, so you might ask the question is like, why these things work only for simple graphs, or why they do not work for weighted graphs? The common barrier, you might search for the common barrier of actually working for weighted graphs. So just 2 remarks actually. If you assume a simple graph, your life becomes a lot easier, because you have a proper bound on the number of edges that is on the graph or any subgraph, so you can do sampling and other things, which are usually done in randomized algorithms. And also, I should mention that all the improvement that I mentioned in the red in the previous slides, they're all improvements on the different simple graphs, and they do not follow the Karger's framework. So they do completely different things. So you might then ask the question, okay, so what is so hard about Karger's framework that we cannot really adapt it to other models, or even we cannot improve it in the sequential model? And that question and the answer to that question is going to be the main meat of this talk. Okay, so at this point, let me introduce a different problem, which is very related to the min-cut problem. This is called two-respecting min-cut problem. So what is the input? As before, it's a graph, but now here is an additional input, which is a spanning tree of that graph. So in this picture, these blue edges actually represent a spanning tree. So you're given a graph and you're also given a subset of edges, which forms a spanning tree. And a two-respecting cut is going to be a cut of the graph where the number of edges of the spanning tree which participates in that graph is going to be at most 2. So if you look at this dotted line, blue dotted line, that's a cut of the actual graph. And the number of blue edges that is cut by this cut is 2. Okay. And now the goal of this problem is to find a minimum to respecting such cut. Okay. Why this is interesting for our problem? Because of some reduction that shows that if you can find an efficient algorithm for solving the two-respecting min-cut problem in any models that we have talked about, then you can actually find an efficient algorithm for solving min-cut. And this, I will not talk much about it, but this goes via something called graph specification. Okay, and we have looked at it, and what we found out is that this is the main bottleneck. We do not know how to get an efficient algorithm for the two-respecting min-cut than what is provided by Karger, and we do not know how to adapt Karger's algorithm into other models of computation. So this is where the innovation comes in, that we have to design an efficient algorithm for two-respecting min-cut. So just to make the point home that this is, if you look at this picture right now, this is not a two-respecting min-cut or like two-respecting cut, because the number of edges of the spanning tree, which is in blue, that is taking part in the cut is 3. So it's like a 3-respecting min-cut, but not a 2-respecting min-cut. We are specifically interested in 2. And why this problem is more structured problem, and the intuitive reason is the following: that okay, so I have written down this is an exponential, like it reduces the search space exponentially. But let me say 1 or 2 sentences about it. So if you look at the global minimum cut, and if you have to naively search for the minimum cut across all possible cuts, how many cuts? What is the cut space? This is like 2 to the power n. So there are 2 to the power n possible cuts, and you have to find the minimum. Whereas in the two-respecting min-cut problem, you have to only search among the cuts which respect the spanning tree in 2 places, like 2 edges of the spanning tree are cut. So how many such cuts are there? There are only n square many such cuts. N choose 2 plus n. So from a search space of 2 to the power n, it sort of reduces the problem to a search space of n square. So but we are actually aiming for more. We are actually aiming for an order n kind of algorithm in different models, and we are also aiming to improve the sequential model in some sense. Okay, so this is what we prove in a nutshell. We give a simple and efficient algorithm for mean two-respecting cut, and this will give you an improved weighted mean cut algorithms for all models. So this is why the almost universal algorithm comes in, because our algorithm is just one schematic algorithm. And you pick your favorite computational model, then that schematic algorithm can be implemented in that model efficiently. And in each of these models, you get actually state of the art. So And that was not the case for Karger. Karger's algorithm can only be implemented in sequential and parallel, whereas our algorithm can be implemented in all of them plus parallel. I skipped that because that won't be a part of this talk. And I just want to mention that there are like also recent work on it, like for the weighted min cut in the sequential model, there is a parallel paper by that has appeared in iCalp and won the best paper award. So this is a very interesting problem. That's the message I want to impress upon. Okay, so just to recap, this is what we are looking at. This is what we're going to talk about. And what we are going to, with the model of computation that we choose for today is called cut query model. Let me quickly define what is the cut query model, then I will just stop to, I mean, you can let me know if you have any questions on it so far. So the cut query model is the following. There are two players, the querier and the oracle. So on the left, there is oracle and the querier on the right, and the oracle has the full graph with them. So the querier can ask the oracle for a cut value. So the querier provides the oracle with a cut. So here in this case, querier provides a cut S1 and S1 complement. And the oracle will give you the value of the cut. Okay. And depending on what the querier gets, querier issues a second cut and oracle gives a value, and so on and so forth. So this is the cut query model. And why this is very interesting to look at, because this is sort of like gives you an abstracted view of searching in the search space. So essentially this sort of like tells you that, okay, I'm not charging you to compute any arbitrary cut that you get for like, I will charge you only once, but how many cuts you have to actually query, or how many cuts you actually have to see to find the min cut. This is the intuitive reason why this model is interesting, and there are other formal reasons for it, and I will not go into them, but for those people who know, this graph cut function is something is a particular function in a family of functions called submodular function. And in the submodular function family, the main question is submodular function minimization. And this cut queries actually mimics that submodular function minimization question very nicely. So yeah, so this is the definition of the model. And for the rest of the time that I have, I'm going to give you an idea, sketch the proof of an order n polylog n algorithm in the cut query model for weighted graphs, for finding the two respecting min cut in a weighted graph. So that's going to be the rest. If you have any question, this would be a nice point to ask, actually.
Hey, I'm sorry if this question looks trivial, but in the earlier two respective min cut problem, you said that the problem is now reduced from like 2 power n to n square. But I still don't know how, because beyond like in addition to the like two edges which belong to the minimum spanning tree, we also need to choose which edges to cut which are outside the minimum spanning tree, right? So, but then like they aren't included.
No, it's a very good point, and I sort of skipped it. So here is the answer. So the two edges that you cut in the minimum spanning tree uniquely defines a cut of the whole graph. And here is the argument. So I'm going to give you I'm going to give you a one-to-one mapping. So suppose this is your spanning tree. Okay, and you sort of assume that you are only going to cut these two guys. Okay, so what I'm going to give you now is a coloring of the vertices between red and blue. And you understand, like if I just give you two colorings of the vertices, that's going to give you a cut, right? Because the red vertices are going to be on one side and the blue vertices are going to be on the other side. That's uniquely defines a cut. So this is the coloring is going to be. You're going to do a DFS on the tree starting from red. And whenever you cross this one of these edges which are cut of the spanning tree are going to change color. So this is going to be blue, 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 and again red. This is red, this is red. You cross the cut over here, so this is going to be blue, blue, blue. So this is a way to color the vertices into two colors given two edges of the spanning tree. And that uniquely defines the cut. So to answer the question that you asked is we do not have to worry about what other edges of the graph we need to cut. The way to view a cut is not a set of edges that you are cutting, but a bipartition of the vertices. And this two respecting min cut is going to give you an unique bipartition of the vertex set. So I hope that answers the questions. If you have it's not clear, please let me know.
Yes, it does. Thank you.
All right, so let me go ahead. So I will take a quick detour right now, and I will just present you with a puzzle. And in the last part of the talk, I'm just going to connect this puzzle to the problem in hand, which is the two respecting min cut. And here is the puzzle. So the input of the puzzle is going to be an n cross n matrix. Okay, you who is going to solve the puzzle, you do not get to see the whole matrix, but you know the dimension of the matrix. And for the time being, let's just assume that this is a square matrix, so n cross n. You know the dimension of the matrix. What I also tell you as a puzzle designer, that this matrix is monotone. What does it mean is that if you look at the minimum entry of every column, and you start from the left and you go to the right, the column minimums never move up in the row space. So they form a sort of like a staircase. I mean, the picture over there, which sort of like exemplifies this. This is a monotone matrix, and here is an example. So if you look at the column minimums, there is 0, 2, 1, and 0, and you can see that 0 appears above 2 in the row space, and 2 appears above 1 in the row space, and 0 appears exactly in the same place as 1 in the row space, but like never above 1. So I hope the definition of the monotone matrix is clear. So your goal is to find the minimum entry of this matrix. And the queries that you can ask is going to be like, you can tell me a cell of the matrix, and I will give you the value of that cell. The question is like, how many entries do you need to find the minimum of this matrix? I will just give you like a few seconds to think about it, if you can already find an answer to it. All right, so let me give you the answer. It's not very hard. I mean, if I just tell you, you will see that, of course, this is the way. So this is what you're going to do.
12? Okay, no.
Go ahead, Girish.
I thought you can just keep querying until you don't need to go back up when you do the query.
So how do you do it?
Okay, I can think of a n squared by 2, not n squared by 2 really. You keep querying in the first column until you hit the minimum in the first column. Maybe you need to look at the entire first column for that. Sure. But in the second column, you only need to start from where you got the minimum in the first column.
Right. But that can be exactly in the same place.
Yeah, that can be exact. Yes.
So this is worst case n square algorithm, right? Like it can be that the first row will have all the minimums.
Yes. In that case, if you already know this, then you will just search the first row, but you will not know whether that is actually the case. But Girish, what you said has some merit to it, because I'm going to give you a different algorithm, but the best possible algorithm, which actually solves it in order n, is something that you sort of like what you said. Okay, but let me give you a much simpler algorithm, and which is going to be something that we're going to use. Okay, so I'm going to give you an n log n algorithm, and this is going to happen by a divide and conquer technique. So this is what you're going to do. You're going to find the minimum in the middle column. Okay, and once you found the minimum, which is in the orange box over here, you know that the minimum on the right hand side is going to be in the shaded region, and the minimum on the left hand side is going to be in this shaded region, right? Let me just get a pen. So what I'm saying is that the minimum in this set of columns cannot be somewhere over here, right? Because that will not be a monotone matrix then. Similarly, the minimum over here cannot be somewhere over here. Again, that won't be a like a monotone matrix. And I'm sort of assuming over here that every column over here has that unique minimum. But let's just work with that. If there is no unique minimum, all you can say is that there exists a minimum in every column in this region. But yeah. Okay, so once you have it, it's not very hard to see that how you're going to do a divide and conquer, right? So you're going to first ask all the entries of this column, find the minimum, and then you're going to recurse on the two shaded region. By doing so, you're reducing the search area by half, right? Because let's say this is like n cross n, right? So this is like n over 2, sort of, and this is also n over too many columns. They're off by a 1. I do not really care about that. And this is, let's say, L, and this is n over 2 minus L. So from n squared, that's the search space, you are now down to n over 2 L plus n over 2 minus L. So which is like n squared over 4.
It is n minus L, right?
Sorry, n minus L, my bad. And so n squared over 2. So you're cutting down the search space by half. So you can only keep on doing it, only log n many times. And every time you do it, in the next phase, what you're going to do is that you're going to find the minimum in this column up to this row, and here also you find the minimum in this column up to this row. So the total number of queries that you have to make is still order n. So log n steps, every time you are making order n many queries, actually exactly at most n many queries. So it's n log n. Is that clear for everybody how this works?
So it gets complicated if you have multiple minimums, right? And since that if there are multiple minimums, you don't know which one to pick.
That's the thing. That's what I was saying. That yeah.
So take the minimum index element.
Yeah, you will know that there, even though there is a multiple minimum, there is going to be one minimum in this column, which is in the shaded region, and that's all you need.
Okay, makes sense. So in the middle row.
Yeah. So in that case, yeah.
So you take the one with the minimum index, maybe. So that
no, essentially what you're gonna do is that if you have multiple minimum over here, let's say one minimum over here, and one minimum over here. Yeah. So your shaded region on the right is going to be up to this part.
Right.
And shaded region on the left is going to be up to this part. So this is going to be this is going to require more care at this point, but it's still doable.
Yeah.
In logging.
Makes sense.
Okay. So this is the footnote over here is something in the line what Girish said. This is not the most efficient way of solving this. There is some other algorithm called SMOC algorithm, which solves it in order n many queries. But we are going to work with this because this is a divide and conquer technique. So it has got the simplicity of divide and conquer, and it's also very parallel in nature. It means that, for example, once you're done with the first step, you can work on the two shaded region parallelly. And these things are going to be useful as we go along. Okay. Now let me connect this to the global minimum cut question, or actually two respecting cut question. So let's just assume that we have to solve a global minimum cut, and somehow we can find a tree, spanning tree T, such that the minimum cut actually two respects that spanning tree. Let's say I give you that for granted, and I also provide you with the tree. How are we going to solve this? So you can look at something called the cost matrix, right? As always, because this is like two respecting cut, so you can put them as rows and columns of a matrix. So here is a graph, and what you're going to put in the rows and columns are going to be the edges of the spanning tree, right? And whenever you in the ith and the jth entry over here, you're going to put the value of the cut, which cuts ei and ej exactly. So this will give you a cost matrix, and obviously, as I said earlier, there are going to be n square many entries over here, and you have to find the minimum of them. And the cut query model actually gives you, because the question that was asked previously, it actually gives you an access to this matrix entry by entry. So you can find one entry by one query. And how are you going to do that? Suppose you want to find the ith and the jth entry, you're going to look at the tree, you're going to find out the bipartition of the vertices which sort of respects ei and ej, and you're going to find the cut, right? I mean, you can ask the query, you can ask the oracle for the value of the cut. Okay, but again, as before, you cannot just go on and ask everybody. That's too expensive. That's order n square expensive. And this is something off topic for today, but I mean, that's the same problem appears also in the streaming model. But there we can actually, in one pass of the streaming, we can compute n entries of it. But again, if you want to do n square many entries, if you want to do a naive search, then you need n many passes, which is way too expensive. So the trick is the following, that so if you assume that you know two paths of the spanning tree where the best candidates are, then the corresponding cost matrix is going to be a monotone cost matrix. What do I mean by that? So here is a graph, and let's say these are the shaded two things are two paths. So this is, sorry, my bad. So this is one path, E1, E2, E3. And the other path is like E1 prime, E2 prime, and E3 prime. Okay, and now if you look at the cost matrix, where in the row space you have the edges of the path 1, and the column space you have the edges of the path 2. And you are only interested in the two respecting min cut, which cuts one edge from the first path and the second edge from the next path. Then this cost matrix is going to be a monotone matrix. This is the claim, and I'm going to spend a little bit of time to prove you that this is going to be the claim, or at least give you a sketch. So let's make life very simple. Let's look at the case when the spanning tree itself is just one path or two paths hanging from a root. So this is the root, and you have two paths, one on the left, one on the right. So so E1 prime, E2 prime, E3 prime, up to E5 prime is a path, and E1 up to E5 is another path. And you and the fat edges, fat black edges, are the non-path edges of the tree, which or non-path edges of the graph. Okay. So now, if you have this problem, and let's say I want you to find the minimum two respecting cut where you respect one edge from the left path and one edge on the right path. So this is the cost matrix. And you sort of see what's happening over here if you have, if you look at, if you want to find structure in the matrix. So this is the minimum entry. This is the minimum entry. This is the minimum, minimum, and minimum. Right? See, they form a staircase. And the question is like, how do I prove it? Okay, so here is how you prove it. So think of the problem in the following way. Suppose I give you just the tree, which is the 2 paths hanging from the root, without any other edges. Okay, without any fat edges. So you start off with an empty matrix. And now I start giving you the non-tree edges. And what you do is that you check how this introduction of this new non-tree edge is going to affect your matrix. So suppose I tell you that I give you this edge 3. So my claim is that it's only going to affect these rows. You're just going to add 3 to these rows, right? Because like if I ask you, what are the 2 respecting cuts over here, which is going to cut this edge 3, then it's very easy to see that any 2 respecting cut that cuts anything over here and cuts something between E2, E3, and E4 is going to count that edge 3, right? The other kind of 2 respecting cuts are not going to count that edge 3 at all. So it's just a row operation where you can do anything on the column space, which is the right side of the tree, and only I to I prime on the row space. This is where you add 3. Similarly, if I give you 4, which is sort of like straddling between left to right, you can make the same kind of argument and show that the green places are the places where you're going to add 4. And similar to the first case, if I give you the edge 10, it's going to be some columns which are all going to be added the value 10. Now, the claim, and it's not very hard to see actually, is that if I give you a matrix which is generated by only these 3 kind of operations, then the matrix is going to be a monotone matrix. Okay, so I won't prove this claim. This is something that you can actually verify within 5 minutes, and this is very simple. But at least that gives you that if I restrict myself only the spanning trees, which is 1 root and 2 paths hanging from it, and we can just, we want to find the 2 respecting min cut over here, we can just do it in order in log n many cut queries. Okay. I will stop for, I mean, if you have any question up to this point, good, this is a good point to ask. All right, so let's just move ahead a bit. Now, okay, so this is what we actually shown that this kind of paths, what I told you is like hanging, 2 paths hanging from the root is a very special case. We can actually do it for any time when we know which are the 2 paths where the best candidates are in. There need not to be a full root to leaf path, but if we know that here is a subpath and here is another subpath, and the 2 respecting min cuts 1 edge from the first subpath and the 2nd edge from the 2nd subpath, then we can find it. But the question is like, we do not know where we do not know how to find these subpaths. You can just go ahead and compare every subpath one after the other, like compare every pair of subpaths, but that again is very expensive operations because there are many ways of pairing up 2 subpaths. And this is what we address in the next part of the talk, which is, I won't take more than 10 minutes, I guess. I can take 10 more minutes. Is that okay?
Yeah.
Okay, so the leftover detail is going to be picking a few pairs of paths. So this part is going to be, this is just, I'm giving you a bit of warning. This is going to be a bit dense, but it will have one technique which I think is going to be very useful for any algorithm designer to learn. And even if somebody is even working towards like competitive programming, this is also, I mean, he or she already knows this kind of technique, or it's a very useful technique for them, which is something that I call as, not I call, this is known as tree decomposition. Specifically, we will look at two kinds of tree decompositions today. Okay, so if this is true, this is a lemma which is not quite true. So suppose you have already done something called a tree decomposition, and what tree decomposition gives you is the following. It takes an input as tree, and it gives you a bunch of paths of the tree with two properties. These paths are edge disjoint, and the union of these paths is going to be the whole tree. So it's like a partition of the edge set, but each part is actually a path. Now, suppose I give you the tree, and you already done the tree decomposition, and somehow, as it turns out, that each path in this tree decomposition can only be paired with one other path. Okay, then it's not very hard to see that you can do the whole thing pretty quickly. You can find the two respective mean cut pretty quickly. How? Because you're going to pair up these paths one after the other. And for each pair, you're just going to run this monotone matrix business. Because the length of, the sum of the length of all the pairs is at most n, and our complexity is also linear in n, near linear in n, then this linearity will actually percolate, and you will have a almost linear time algorithm. But the point is that this is not quite true, and I would wish to be true, but it's not quite true. And but here is an example where this is actually true. And why? And for that, let me introduce this new kind of graph or a tree. It's called star graph, which is a very simple construction actually. So here is the graph is the tree is just one root over here and edges that is hanging from the root. Okay, and you have to and all the black edges over here are the non-tree edges. Now in this thing, if you look at the cut value when you are cutting E3 and E4, it's not very hard to see that this is the expression. This is the degree of 3, all the edges that is going out of 3, plus all the edges that is going out of 4, minus what you overcounted, or what you actually counted which should not be counted, which is the edges like 3, 4 kind of edges, right? You counted this twice, so you have to remove them twice. So this is not very hard to see. So, but this will give you something interesting. So suppose we are only looking at the cut values, like cut E3 and E4, which is actually smaller than the degree of 3 and the degree of 4. Suppose this is what we want to look at. Then if you just put it in the previous equation, you will see that the weight of this edge, the 3, 4 edge, is going to be strictly more than the total degree of the third vertex, or and strictly more than the total degree of the fourth vertex. Right? So look from the point of view of the tree. This, when I tell you this vertex 3, this actually uniquely specifies one path of the graph of the tree, right? Which is just an edge, root to 3 edge. Now, if I am only interested in this cut E3, E4, which are the only kind of two respecting cut, then you know that 3 should pair up with somebody which has got strictly more than half of its degree going towards. But how many such vertices are possible? There is only one vertex. At most, one such vertex is possible because this is strictly more than the full degree. So E3 can only pair up with 4 over here. So what I'm trying to say over here is that because we have this star structure, every edge, which is also a path of the tree, can only pair up with at most one other edge. So these pairings are very structured, let's put it this way. And so that lemma that I've written down on the top is actually true for star graphs. But usually they are not true. So each path can be paired up with many paths in your tree decomposition, but the kind of paths they can pair up with has a structure. So if you look at a path, the claim is that it can pair up with only one root to leaf path. Okay, this is one idea. And the second idea is that if you look at any tree decomposition, the number of component paths in any root to leaf path is actually log n. So very small. So what you have over here is that not the blue lemma, but the green lemma, which says that every path can be paired up with log n many other paths, which is not too bad. And so you get like a log square n overhead in the overall computation, but that's fine. So I will just give you a very fast recap of the tree decomposition, then I will just flash you the algorithm. There's nothing, I do not expect that you will get something from the algorithm, but that I just want to flash you the algorithm so that you get an idea of how small this is. But let me give you a lightning fast recap of the tree decomposition. So as I said, a tree decomposition is a decomposition of the tree into disjoint paths, and with the property that every root to leaf path is going to have at most log n many component paths. How do you do this tree decomposition? There are two ways that I know of, I can present today, and one is called heavy light decomposition, and this is very simple. What you do is that here is a tree, that's the green that you're given to you. You're going to start from the root and you're going to traverse, and you're always going to traverse to the child which has got more leaf nodes. Okay, so this is the path you traversed, and here you end up with a vertex where both the children have the same number of leaf nodes, or actually same number of nodes in the subtree rooted at them. This is where you stop, and you declare this orange path as one of the paths in your decomposition. Once you have that, you recurse on these two orange guys and whatever is left of the green, and you keep on doing it. It's not very hard to see that you can only do it log n many times. So every root to leaf path over here is going to be broken down into log n many subpaths. There is another thing called biodecomposition, which I'm not sure I have time to talk today, but this is something that you can find. I can at least give you where you can find this. If you look at Karger's paper, where he gives the near linear time algorithm, the decomposition that he uses over there is called a biodecomposition, and somehow it has got the same property, same two properties over there, although it does a very different kind of decompositions. So this is the whole algorithm. I will not go in the full detail of the algorithm, but usually it's the marrying of the two ideas that you have three ideas mainly. You decompose the tree into subpaths, you pair up these subpaths, and then each pair you're going to run this monotone matrix business. Okay. Now, so this is in cut query. I have assumed that you can actually find the value of a cut with just one query. But that's not always the case, right? If you look at sequential model or like normal computation, which you have to code up, you actually have to work hard to find the value of the cut. So, or even in the streaming. So this is what it is right now. In the normal sequential model, you can actually mimic this cut queries very efficiently by something called a range operation data structure. This is again a very useful kind of data structure and a very versatile data structure. And if you are trying to design some fast algorithm, this is something you should definitely look at, how this range operation data structure works. But what it gives you is that you can actually simulate every cut query in log n time, order log n time, with some amount of pre-processing. In the streaming, however, you can simulate order n many cut queries in one pass, and because we have used the divide and conquer technique, and the rest of the algorithm is parallel enough for us to just get the streaming algorithm in total log n many passes. Okay. So this is a summary. Let me quickly summarize what's going on, or what we have talked about today. So this is the first thing. We are supposed to solve the global minimum cut. This is the goal that we started off with on weighted graphs. So the first thing is that to reduce the problem to a two respecting min cut problem. This is something we skipped, but this is something that is done by something called cut sparsifier and spanning tree packing. This is efficient in all the models, and you can just look it up in Karger's own paper, actually. This is not something that we improve upon. But once you have this two respecting min cut, we try to solve it very efficiently. And when the spanning tree is just a path, we can solve it by using the properties of the monotone matrix. When the spanning tree is a star graph, we can solve it by just quickly using this edge pairing, that one edge can only get paired with at most one other edge. And when it is a general spanning tree, we have to do some more tricks, which is the tree decomposition, and we have to use this almost correct lemma that I mentioned. But again, the meat of the matter is that you again sort of reduce the problem to monotone matrix, minimum in the monotone matrix computation. So that's all I wanted to say about this algorithm. I just mentioned a few open problems, and then I will close. One question that is very close to my heart is just the graph problems in the two-party communication setting. I haven't defined this setting, but it's not very hard to find a definition in any standard textbooks or even in Wikipedia. But it's a very, very interesting setting and a very powerful setting in which we do not know much about the efficiency of graph problems. This is something that I think is very important to study. Another direction would be to study the min-cut problem in the dynamic setting. In a dynamic setting, you are given an input, you compute the min-cut, but now the input might change. So you get updates on the input that some edges might vanish, some edges might get bigger, and so on and so forth. And the idea is that you cannot keep on computing min-cut afresh every time an update comes. So you have to somehow compute the min-cut in such a way that you can tackle with small perturbation of the input. And you can, every time with a little bit of post-processing, you can again find the min-cut. Our algorithm is sort of, I do not see how to adapt this algorithm immediately to the dynamic setting, so that's an important question. Another thing is like something that we skipped today, which is the first part of the algorithm, which is the cut sparsifier. Whatever we said after the cut sparsifier is a deterministic algorithm. The cut sparsifier is the only part which makes it randomized. So if there is any way that we can make cut sparsifier deterministic, then we have a deterministic algorithm. And the fourth one, which is the hardest one of all of them, is going to be look at the directed version of this problem where you have direction on the edges. And you can look at vertex connectivity as well, which is sort of like a directed min-cut. This is a completely different beast altogether. And none of the things that we have said today works immediately to the directed version of the min-cut. So I will leave you with this four directions of the open problems, and I will stop here. Thank you. If you have any questions, I will be happy to answer.
So I have a question. Thank you. Sagnik, what do you think the graph problems in two-player communication setting?
Yeah, so that's why I kept it a little bit vague, right? So there are many ways you can pose graph problems in a communication setting. Let me give you one. Okay, so let's say you want to look at, let's say, min cut problem. Okay, whatever we talked about today. What happens is, like, in the two-party setting, Alice gets a bunch of edges and Bob gets the rest of the edges. And now they have to find the min cut. The number of edges that Alice gets and also the number of edges that Bob gets is not going to be small, so that Alice can just send across those edges to Bob, when they are going to be pretty dense. So you need a lot of communication to do it naively. But let me just tell you in advance that take our cut query algorithm. You can just simulate it in the communication model, and that will give you an n polylog n time communication, because you can simulate one cut query very quickly in the communication model. But this is just min cut. You can ask this question for any graph problem. And nothing substantial is known. I mean, there is a lot of gap between lower and upper bound. So that's the setting. This is one of the settings. There are also other settings where Alice gets a bunch of vertices and all the edges incident on them, and Bob gets the rest of the vertices and all the edges incident on them. That's a different kind of setting. So yeah, any of them would be useful.
What is the lower bound node? Just curious.
Yeah.
For some cases, yes. Let's say for this min cut problem, even for connectivity problem, just you want to check whether the graph is connected or not. You can prove an omega n lower bound. For matching also, you can prove an omega n lower bound, and there is no cookie for guessing which problem you reduce it to. Which problem reduces to that problem. Of course.
Which one?
That is one.
The disjointness is the complete problem for communication.
Yeah, it is. Yeah, but omega n lower bound is not sufficient, right? Because the input size is much larger. So an omega n lower bound will not give you much.
So you said that, like, intuitively there is an omega n lower bound, but I mean, is there a formal proof for an omega n lower bound?
For some problem, yes. Yes, like you can reduce set disjointness to this problem. For min cut or connectivity, let's say, there are formal proofs of reduction. But I mean, are you talking about communication or are you talking about sequential?
Communication.
Yeah, communication, there are formal proofs. But sequential, I do not know what you can get. Maybe if you assume SETH or ETH or something like that, you can get something out of it. I'm not sure.
If you could reduce, when you are able to reduce disjointness, then it says that it's hard in even random setting, right? Means in a randomized.
Yeah. Yes. But not in quantum setting. So you have to work with the inner product mod 2 functions over there. So quantum lower bounds are also known.
I see.
In quantum, disjointness has a better protocol, is it?
Yeah, the order square root n protocol.
Oh. Nice talk. It was, yeah, very nicely presented. It's
Thank you.
very accessible.
Yeah, I was trying my best to actually get something to also the students. At least they can think about one problem which is easy to state, which I thought, like, two respecting problem is pretty easy to state. And the algorithm, at least for the monotone matrix algorithm, is not too hard. So there is something that they can take away with.
Nice puzzle in between.
So are there lower bounds in these models, or means like does your algorithm like matches the lower bounds, or is there a gap?
There is a gap of log.
Or log factors.
So in CONGEST model, you had root n plus d, right? Polylog. So which is like close to 10 lower bound.
In CONGEST model, it's tight. But in other models, there is a log factor gap, a log and polylog factors gap. And I think those gaps are important. I just want to make sure that you just do not like throw away like, it's log factor, who cares? No, there's a very interesting gaps over there. And I'm pretty sure if you can block those gaps somehow, you're going to get very interesting techniques, because I do not think any current technique works to block those gaps.
I see.
So I was wondering, so there is this connection between max flow and min cut, no?
Right. So, that's the ST version.
Yeah. So I mean, so these some of the results is also applicable to finding the max flow also.
No, that's what I wanted to mention in the beginning, that whatever I'm going to tell you is about global minimum cut, not ST minimum cut. Unless you have something for ST, you cannot get max flow.
I see.